We're always hearing about the insane GPUs and the massive datasets that are driving this whole AI revolution. But what about the invisible stuff, the infrastructure that connects it all? Today, we are going to focus on the network, the unsung hero that can either make your AI fly or become its biggest bottleneck. It is literally the nervous system of your AI cluster, and getting it right is more critical than ever. So, let's dive in.
And yeah, this quote just hits the nail on the head. The stakes are incredibly high. You see, in today's shared AI data centers, the network isn't just some plumbing. It's a massive strategic asset. Get it right, you unlock incredible efficiency. Get it wrong? Well, you create a huge bottleneck that just grinds innovation to a halt and wastes a ton of very, very expensive resources.
So here's how we're going to tackle this. First, we'll talk about the new reality of the AI data center. Then, we'll get into the tough challenges this creates for networking. After that, we'll compare the main technologies out there, do a deep dive into this really cool concept called cell spraying, and finally, we'll deliver the strategic verdict on the best way forward. Okay, first up, the new AI data center. The old way of doing things, dedicating an entire cluster to a single, massive job, that model is basically dead. The economics just don't make sense anymore.
No, today it's all about the multi-tenant AI cluster. What that means is you've got a single, shared fabric that has to juggle everything all at once. We're talking training massive foundation models, running real-time analytics, and doing complex simulations, all at the same time. This kind of chaotic mix creates a super dynamic environment that puts just extreme pressure on the network. And, this new world brings a whole new set of fundamental challenges that any network solution absolutely has to solve. It's this really delicate balancing act between raw performance, keeping users separate from each other, and of course, being able to scale without everything falling apart.
And here they are, the 8 critical demands. I know, it looks like a laundry list, but trust me, every single one of these is a must-have. You need ironclad isolation to stop those noisy neighbor problems. You need smart load balancing for traffic you can't predict. And you need it all without the performance hit you get from old-school software overlays. The network's got to handle any packet size, support any protocol, recover from failures instantly, and scale like it's nothing. It's a really tall order.
So the big question is, with a wish list that demanding, how do the networking technologies out there right now actually stack up?
All right, let's get into the contenders. We're going to take a totally impartial look at the 4 main approaches on the market, breaking down the good and the bad for each one. First up, the classic, InfiniBand. It's been the go-to for high-performance computing for a long time, and for good reason. It's got ultra-low latency and native RDMA support, which lets servers talk to each other without bogging down the CPU. But it has some major downsides for modern AI. It's a closed, single-vendor ecosystem, which makes it a pain to scale, and trying to isolate tenants means adding these clunky, slow software layers on top. Next is standard Ethernet. It's everywhere, right? It's affordable, it's interoperable. The problem? It was never, ever built for the brutal, all-out nature of AI workloads. It's super prone to congestion, and trying to tune it for high-performance stuff like ROC, that's basically RDMA over Ethernet, can become a full-time job for an entire team of experts. No joke.
Our third contender is something called endpoint scheduled Ethernet. The idea here is to use smart NICs to manage traffic right at the server, which makes things more predictable. But, and this is a big but, it essentially marries your servers to a specific high-end network card. This tight coupling just adds a massive layer of complexity as you scale, making it an absolute nightmare to manage in a diverse, multi-tenant setup.
Okay, so this table really lays it all out. You can see InfiniBand is fast, but it gets super complex with multi-tenancy. Standard Ethernet is open, but it's always reacting to congestion, not preventing it. Endpoint scheduling gives you more control, but it adds a ton of complexity. But then, look at that fourth column. Fabric Scheduled Ethernet. It's native for multi-tenancy, proactive on congestion, and optimal for load balancing. This points to a fundamentally different and, frankly, better design. So what makes that last one so special? Well, let's zoom in on a key piece of the puzzle. We're going to do a quick deep dive on a concept called cell spraying. This is the secret weapon behind that optimal load balancing we just saw. So, what on earth is cell spraying? It's a surprisingly simple yet incredibly powerful idea that's unique to Fabric Scheduled Ethernet. Instead of trying to send a whole big data packet down one path,
It chops it up into these tiny, uniform pieces called cells. Then it just sprays those cells across every single available network link at the same time.
And this is why it's such a game changer. It takes a massive elephant flow of data, chops it into tiny cells, and sprays them perfectly evenly across every path it can find. This completely eliminates bottlenecks. So no more a single clogged-up path while other links are just sitting there doing nothing. Every part of the network gets used perfectly. And the best part? It's all automatic. Zero tuning, zero tweaking. It just works.
All right, let's tie this all together for the strategic verdict. Because as we've seen, this isn't just some technical choice. It's absolutely mission critical for your entire AI strategy. Let's talk real-world impact. A tiny 1 to 2% network slowdown during a training job doesn't sound like much, right? Wrong. That translates to hours of lost compute time. Now multiply that across thousands of incredibly expensive GPUs, and every single percentage point of inefficiency is like setting fire to a mountain of cash. You're not just losing time, you are actively burning money. And really, this all comes down to a fundamental difference in design philosophy. Traditional architectures, they try to bolt on features like isolation after the fact, which just adds complexity and a performance tax. Fabric Scheduled Ethernet, on the other hand, was designed from the ground up for multi-tenancy. Isolation is baked right into the hardware, with zero overhead and absolutely no manual tuning needed. So, what you get with this native design are 4 huge advantages. A deterministic, lossless fabric for any kind of workload, native multi-tenancy for simple, rock-solid isolation, full fabric utilization because of cell spraying, and extreme resilience with super-fast, hardware-based recovery to protect your most important jobs. So the verdict is pretty clear, isn't it? For the insane demands of modern multi-tenant AI, Fabric Scheduled Ethernet just stands out. It's the only solution that was purpose-built to accelerate AI innovation, turning the network from a painful constraint into a powerful catalyst. Which leaves us with one final question for you to think about. Is your network a catalyst for innovation, or is it a constraint that's quietly holding you back? The answer to that is going to define your success in the age of AI. Thanks for watching.